Hello, AP Chemistry, and welcome to Quantum Mechanics and Atomic Orbitals. So, in the previous one, we talked about how, two ago, we talked about the wave nature of light, okay? Then we also talked about how matter can also behave like waves, right? So now, all of that kind of comes together, right? And it comes together in the quantum mechanical model of the atom, okay? Wherein we say that our electrons can behave kind of like light, and move in waves, kind of like a particle. All right, and it gives rise. The quantum mechanical model refines the Bohr model such that instead of having orbits, right, these circular rings that the electrons revolve around, instead of having that, we move to the concept of orbitals, right, where an orbital, which is really just an area of electron density, okay, and it's a place where we'll probably find an electron. All right. Note that it doesn't say anything about how an electron moves or where an electron is going, right? All it does is it tells us that this is the high probability area for finding an electron. These are my low probability areas, right? And eventually, right, if we go out far enough, there is a no probability area, okay? And this is what orbitals are, okay? Where we might find an electron, okay? So when we say that orbitals have specific shapes, we're just saying that those are the specific regions in three-dimensional space where we might find an electron, okay? Useful to know, right, that electron density is also known as psi squared, right? That's the symbol that stands for that. Now, everything that we are going to talk about in terms of atomic orbitals happens to be solutions, like numerical solutions to the Schrödinger wave equation, which is math beyond what we're going to do at this point in time, okay? It's like multivariable calculus. But suffice it to say, these are solutions to that equation, which is why we have numbers that stand for pieces of information, okay? So here is a simple and quick table that sort of defines our relationships for our quantum numbers, okay? Here we have a quantum number n, which stands for our shell, okay? So we could also say energy level. That would be okay also. So shell or energy level is denoted by n, okay? 1 is the first one. That's the one closest to the nucleus. 2 is further, 3 still further, 4 even further still, okay? Now, every n has a certain number of possible values of L, where this is the angular momentum quantum number. L is the angular momentum quantum number. All right. And again, we have some numbers here, right? And this ranges from 0 up. This starts from 0 and ranges to however many my shell has, right? Which is why shell 1 can have one possible value. 2 has 2, 3 has 3, 4 has 4. Okay? And note that these values correspond to subshells, right? In that, if we take a look here, right, 0 corresponds to an s orbital, right? 1 corresponds to a p orbital, right? 2 corresponds to d orbitals, and 3 corresponds to f orbitals. Okay? And again, note that we always start with s and work our way up. So shell 1 has an s orbital and only an s orbital. Shell 2 has an s and a p. Shell 3 has an s and a p and d's. 4 has s and p and d's. Okay? And after d, I guess, they do go alphabetically. In that if we had a 5, right, 5 would have s and p and d and f and, right, G, okay? All right, moving along. So here, right, this should look very familiar because we talked about this part last year, right? Here we have m sub L, which corresponds to the actual number of orbitals, okay? So m sub L corresponds to the actual number of orbitals. So if we look, right, if we have an s orbital, there is one orbital, okay? No, that's not what I mean to say. If we have an s subshell, by the way, that's what that stands for, right? If we have an s subshell, we can have a total of 1 orbital, okay? If we have a p subshell, we can have a total of 3, right, which goes hand in hand with these values right here. D orbitals can have a total of 5, f orbitals can have a total of 7, right? By that thinking, g orbitals would have a total of, right, g orbitals would have a total of 9, okay? So then every shell has a certain number of subshells. Every subshell has a certain number of orbitals, so that every shell has its own different total number of orbitals, okay? And every orbital can hold a total of 2 electrons. Yes, going back to last year. So, shells, subshells, orbitals, and every orbital can hold 2 electrons. Okay. Now, that brings us to the last quantum number, which isn't in that last diagram, and the last quantum number is our magnetic spin quantum number, denoted m sub s. All right. And this is where we get the idea of drawing our electrons as opposite pointing arrows. In that experimentally, right, scientists understand that when we take electrons and we put them through a magnetic field, a strong magnetic field, they will divvy into 2 separate piles, or 2 separate paths, I guess would be better to say. 2 separate paths. And we arbitrarily denote them, right, as these different arrows, right? And we give them these values of +1/2 and -1/2. And these are arbitrarily assigned numbers that just sort of help us to visualize what we mean, okay? So, if we were dissecting this diagram of energy, right, lowest energy, we would start with our 1s orbital, right, where 1 indicates my, right, 1 indicates my shell, s indicates my subshell, this is my orbital into which I could put 2 electrons, right? This is, again, energy, this is shell 2, subshell s, total of 1 orbital. This is shell 2, subshell p, total of 6 orbitals, 3 orbitals, which could hold a total of 6 electrons, so forth and so on, okay? All right, so finally, in terms of what you need to know, right, you need to know that N, right, stands for our shell. We could also call this our energy level. And this starts at 1 and works its way up, where 1 is closest to the nucleus, and they get progressively further from there, right? You need to know that N, after N, we have our subshells, right? And every subshell has a certain number of actual orbitals that compose it, right? And then we also have our spin, right, which says that we have up arrow or down arrow. And this actually is the result of the Pauli exclusion principle, which states that no 2 electrons in an atom can have the same 4 quantum numbers. No 2 electrons in an atom can have the same 4 quantum numbers, where N is 1 quantum number, L is another quantum number, M sub L is another quantum number. So these 3, right, an electron can have the same shell, same subshell, and be in the same orbital, but they're going to have opposite spins. Okay, and that's what the Pauli exclusion principle states. All right, so this is an introduction to the concept of orbitals. In the next one, we're going to talk about what those orbitals look like, and then we're going to start writing some electron configurations. All right, thanks for listening. Be good, and I'll see you soon. Bye.